Hello, I'm Sylvia Knight, Head of Education at the Royal Meteorological Society. In this series of short films, we're going to be covering some of the background information that teachers may find useful if they're teaching weather and climate at secondary level, and specifically if they're using our weather and climate teaching guide with the accompanying classroom resources, which you can find on our website MetLink. In this film, I'll be looking at the climate of hot deserts. The global atmospheric circulation, which we talked about in an earlier film, suggests that at the edges of the Hadley cells, sinking air leads to high pressure and clear skies. These subtropical regions are the source region for any tropical, continental or maritime air reaching the UK. Seasonal shifts in the latitude of the intertropical convergence zone as the sun moves from being overhead at the Tropic of Cancer to being over the Tropic of Capricorn affect the location of the high pressure belts. High pressure is linked to clear skies and little precipitation, so the Earth's hot deserts are located in these regions. The Atacama Desert is the driest non-polar place on Earth, found along the western edge of South America, between the Andes and Chile's coast. The average rainfall is only 15 millimetres per year, with some places receiving as little as 1 to 3 millimetres. The aridity is partly due to the cold Humboldt Current, which flows along the nearby coast. Little evaporation occurs from the cold water, and the current contributes to a temperature inversion, so air cooled by the surface cold waters is trapped below warmer air, meaning that there's little convection and cloud formation is suppressed. However, during an El Niño event, the normally cold waters in the East and South Pacific warm dramatically, and this can lead to warmer, wetter conditions in the Atacama Desert. During the strong El Niño event of 2015, 23 millimetres of rain fell in a single day, and this led to a desert bloom, the flowering of flowers whose seeds had lain dormant for decades. El Niño is one half of the El Niño Southern Oscillation, or ENSO, which gives the whole world El Niño or La Niña weather patterns. These are centred around the equatorial Pacific, where the easterly trade winds normally blow the warm surface water from the eastern side over to the western side, leaving the water around the western coast of Chile and Peru relatively cold. Every few years, a very noticeable change comes about. The trade winds weaken, allowing the warm surface waters to surge back. The eastern side, which is usually the coolest part, warms up considerably. With warmer surface water, more evaporation can occur, and so the rainfall in that area also increases. On the other hand, the western side gets cooler and drier. This shift has a big impact on land regions bordering the equatorial Pacific. Northeast Australia and Indonesia and Papua New Guinea become much drier, whilst coastal parts in Peru and northern Chile, which are usually rather dry, experience much more rain. This increase in Eastern Pacific Ocean temperature is known as an El Niño event, which means the boy child in Spanish. The opposite phenomenon occurs when the eastern equatorial Pacific becomes even cooler than normal and the west becomes even warmer. This leads to flooding in Indonesia and eastern Australia and drought conditions in Peru and northern Chile. This state of the ocean is known as La Niña, or the girl child. On this graph, the red areas show El Niño conditions, whereas the blue regions show La Niña, and you can see that the Earth is frequently shifting from one to the other, but it's not a regular pattern, and how long the conditions last is quite variable. Both El Niño and La Niña affect weather patterns far beyond the equatorial Pacific, as the whole global pattern of winds and precipitation in the atmosphere adjusts to the changes in the Pacific. In fact, the average temperature of the atmosphere averaged around the whole globe tends to be much higher than normal in the months during and immediately following an El Niño event, as vast amounts of heat are transferred from the ocean into the atmosphere. In the UK, we tend to see more storms in late winter during La Niña conditions, but we can have colder late winters during El Niño. In 2021 and 2022, we had an extended period of La Niña conditions, which meant that even though global warming meant we were in the 8 warmest years on record, temperatures weren't quite as high as they might have been. The El Niño conditions in the second half of 2023, combined with global warming, made 2023 the warmest year ever recorded. We don't really yet know how ENSO itself will be affected by global warming. We talked about the Milankovitch cycles in the past climate change film. They lead to different patterns in the sun's energy reaching the Earth. On timescales of 40,000 to 100,000 years, the most visible impact of these is near the poles, where the total amount of ice changes in response, causing glacial interglacial cycles. In the tropics, where the temperature doesn't change so much through the year, rainfall determines the seasons. The tropics are much more influenced by changes in the orbital precession, which is another of the Milankovitch cycles, which has about a 21,000-year cycle. This cycle shifts the main band of rain, the intertropical convergence zone, either further into the northern hemisphere or into the southern hemisphere. Around 12,000 years ago, monsoon rains penetrated its furthest north. One consequence of this was more moisture making it into the Sahara Desert. With the greater moisture, plants were able to grow. This greening of the region led to climate feedbacks. As the land cover changed colour, there was even more moisture recycling. This changed the Sahara from desert to shrubland, and a burgeoning population of hunter-gatherer fisher folk lived in the southern Sahara until around 7,000 years ago, at which point they were replaced by early pastoralists, who probably imported animals from the Fertile Crescent, which is in present-day Iraq, and also farmed locally domesticated cattle. Some rock art remains as a legacy of this period. Unfortunately, the Milankovitch cycles were working against them, and as the orbital precession changed, the monsoon rain band retreated back towards the equator. Around 5,500 years ago, the climate vegetation feedbacks were not strong enough to maintain the moisture needed to support shrubland, and the region abruptly changed back to desert. The resultant immigration into the Nile Delta out of the newly formed Saharan desert is thought to have been a catalyst of the ancient Egyptian civilization. The 2021 Intergovernmental Panel on Climate Change report concluded that as the climate changes through the 21st century, we can expect to see the Hadley cell broaden and the rainfall zones associated with the intertropical convergence zone become narrower. As a result, some arid regions are expected to grow in size. This effect can be enhanced by deforestation at desert edges. The IPCC's 2019 Special Report on Climate Change and Land concluded that saying whether desertification is occurring due to climate change or due to other human activities depends on the location and varies with time. Climate change will exacerbate several desertification processes, and as the climate changes, the risks associated with desertification increase. Desertification and climate change, both individually and in combination, will reduce the provision of dryland ecosystem services and lower ecosystem health, including losses in biodiversity. Increasing human pressures on land, for example through population growth, combined with climate change, will reduce the resilience of dryland populations and limit their ability to adapt to the changing climate conditions. Desertification exacerbates climate change through several mechanisms such as changes in vegetation cover, sand and dust aerosols, and greenhouse gas fluxes. In some places, the ability of vegetation to remove carbon from the atmosphere is limited by the availability of water rather than the air temperature. In these areas, net carbon uptake is about 27% lower than in other areas. The extent of areas in which dryness, rather than temperature, control carbon dioxide exchange has increased by 6% since 1948 and 2012 and is projected to increase by at least another 8% by 2050. Site and regionally specific technological solutions based both on new scientific innovations and indigenous and local knowledge are available to avoid, reduce and reverse desertification, simultaneously contributing to communities' ability to prevent or mitigate climate change and to adapt to the consequences of it. Investments into sustainable land management, land restoration and rehabilitation in dryland areas have positive economic returns for the local people. Policy frameworks promoting the adoption of sustainable land management solutions contribute to addressing desertification as well as mitigating and adapting to climate change, with co-benefits for poverty eradication, food security for the dryland populations. Improving capacities, providing higher access to climate services, including local level early warning systems, and expanding the use of remote sensing technologies are high return investments for enabling effective adaptation and mitigation responses that helps address desertification. NASA is a good source of global temperature and precipitation data and maps, and earth.nullschool.net is a good way of exploring current conditions. In the next film, we'll look at the changing global climate.